So, okay, so we are here for a zkStudyClub. It's been a little while. I think it's been like a couple months since our last one. And for this session, we have Izaak Meckler from o1Labs, who's going to be talking about Pickles. He's going to be doing an overview into the entire concept and then look into the techniques and some of the lessons that were learned along the way. There is, just FYI, a bit of a lag on this. So if there's some awkward pauses, that is because there might be some sound delay through the Zoom call. But Izaak, if you hear me, if you're good to go, then take it away when you're ready.
Cool. Yeah, thanks, Anna. Yeah, today we're going to be talking about Pickles. It's basically a new snark construction, which is based on a lot of work that others have been doing as well, and a library. What's significant about it is that there's no trusted setup. That's like what's most significant for us, like working on Mina, or what used to be Coda. It has a pretty small proof size, compared to some of the other systems that you might see out there, like Starks, for example. The provers is quite fast, and the batch verifier is quite fast as well. And then the thing that I'm sort of, that I really hope other people learn from, especially, is there's a really nice interface for doing recursion. And I think it's sort of like it's a great way to program with recursion. I recommend people do it. So let's talk about the kind of ingredients that go into this snark construction. There's sort of two sides. There's the crypto side and then the software engineering side. So on the crypto side, there's Halo type batching technique, or what are people calling it? Accumulator technique. And curves that Dara constructed, a kind of Planck system with specifically tailored custom constraints, and a very sort of tuned Poseidon hash function. On the software engineering side, yeah, there's this sort of kind of really nice simple recursion proof composition interface, and also backwards compatibility with ranking constraint systems and all of the other kinds of constraints that we were using already in, if it's confusing to people, so I used to work on a project called, I worked on a project that used to be called Coda, and now it's called Mina, so I'm the same Mina. So this backwards compatibility is really essential for Mina because it means we didn't have to scrap anything. So I might also talk a little bit at the end, if there's time, about snaps, which are essentially snark-based kind of smart contracts on Mina, and that's what we're using Pickles for also. Okay, so I probably don't need to do it for the people here, but maybe I'll just do it for the sake of the video, because I watched some other ones and everyone else did kind of an overview of what snarks are, so I guess I will too. Right, so the kind of ideal functionality that snarks provide are you're a little verifier, and you want to learn some truth, some statement, and somehow some god or something sends you down a proof, which is sort of on your scale, not on the scale of a god who can comprehend the real facts that would lead you to believe the statement, and the verifier can be convinced of this statement without having to sort of be a god, shall we say. And what's cool about snarks is, even if you're not really talking to a god, but you're talking to some devil, you can also still be convinced, and there's no way the devil can trick you. So, in reality, at least I haven't had experience with the gods or devils. There's just people, and you want to learn some knowledge produced by some other people in reality. So these proofs are not really produced by gods or even devils; they're produced by other people. This to kind of motivate recursion. Think about, you're a student and you want to learn a very refined idea, but that refined idea, it built on say the sum total of human knowledge, and so it's not really reasonable for you to sort of reread all this yourself. That would be too hard. It would take too long. So, the ideal situation would be we can call up some god, and they would, compress down the sum total of human knowledge into some little proof whenever we need it on demand, and we could just hand that to the student. But, that's kind of expensive because it's very, we don't get to talk to a god very often. So what we would really like is some way that even if like later, someone kind of makes some partial progress, like they build on top of this idea, we don't then want to have to go call a god again and have them recompress the whole pile, because, ideally we could just sort of update what the sort of proof that we got from the god prior, and without having to recontact them. It's very tricky to contact a god. So what kind of saves you in this situation is that very often your computations will be sort of have some kind of local structure, where each part of the computation only depends on a small amount of information from other parts of the computation, shall we say. And, so what this looks like is you sort of have all these little provers, maybe greater than the student, but not so much greater, who throughout time build on each other, and at the end, they sort of have some way of combining all of their knowledge across time, and they can give you the latest knowledge, easily digestible at any given moment. Okay, so that's some kind of silly motivation. Right, so the usual setting with a snark, you have a statement, and you get some proof corresponding to that statement, and then you can easily check this proof statement pair. With recursive snarks, what that lets you do is basically take the previous proof and previous statement and kind of update it. So let's see. So suppose we had some statement S1 and that arrived at the first moment, and then later on we get some statement S2, and we would like to prove their conjunction, S1 and S2, say, without having to do all of the work that was required to produce this proof pi1. So what recursive snarks enable is the ability to do just this, to basically reuse the computation that was done previously to produce pi2, or pi1 rather, in producing this new statement, which is sort of composed of the previous one and also some new information. And that can just go on and on. So like then sometime later, a proof S3 comes around, and we can prove some statement, say like S1 and S2 and S3, while only relying on pi2, not having to go all the way back and redo this computation or redo this computation, or even to look at this proof necessarily. So to kind of sum it up, recursive snarks, or recursive composition of snarks, is useful for when you want to prove a sort of ever updating, usually kind of over time, statement in such a way that the previous proof can also be updated along with the statement without having to sort of redo all the work. And just to make it maybe a little bit more concrete, with snarks, we know, let's say you could prove a statement of the form, iterating f for 1,000 yields 43, like f of f of f, blah, 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 of 0 or something equals 43. And we know with snarks, like even if this took 1,000 years, you could convince someone easily that would be true. But with sort of vanilla snarks or whatever, if then you wanted to say, but if you do it for 1,001 years, you get 45, you'd have to redo the whole computation.
I think we lost your audio.
It's going to work this time, I can tell. Cool. So yeah, we were talking about, like, let's say you wanted to prove to someone, like, yeah, if I iterate this function for 1,000 years, like you get 43, then you wanted to run it for another year. With regular snarks, you just have to recompute everything from scratch. With recursive snarks, you can do this kind of o1 update, where you can reuse the computation that you did before with the old proof to produce this new proof that has this sort of extended information. Cool. So, and like the kind of example that is, I don't know, my day-to-day example is you would have a statement like there is a blockchain of length 1,000 such that the final state is S1. Then, you know, you'd want to add one block and prove there's a blockchain of length 1,001 such that the final state is S2. I mean, you wouldn't want to have to recompute everything. Cool. So I'm just going to move on a little bit just for time. We can go back maybe later. And I will give a little bit of a brief review on accumulation. Dara, what is this called? Accumulation scheme? Accumulation?
Yes.
Yeah, something like that. So this is a technique for doing recursion. It's like the halo technique, and it's very important. So let's say that we have like a narc, which I never heard anyone say that, but would be like a non-succinct snark.
I say that.
You say narc?
Yes.
Okay, yeah. So we have a narc where the verifier has sort of two components. It has a fast part, v sub f. And when I say fast, I'm saying like, you know, the real relevant metric is like arithmetic circuit complexity, but, you know, we can sort of imagine in our minds, the fast part is like 1 to 30 milliseconds, let's say. And then there's the slow part, which is like 100 milliseconds to like a second or so. And the verifier has this structure. And moreover, there's sort of an update algorithm, which, and a notion of like a proof state, okay? Such that instead of, you know, when you want to verify a proof pi1, instead of running both the fast part, VF, and the slow part, you can just run the fast part and sort of run this update algorithm to transform your proof state S0 into a new proof state S1, which then later, if the mood strikes you, you can feed into vslow, the slow part of the verifier, and sort of finish off the verification. But crucially, you don't need to do that if you don't want to. So let's say, you know, then let's say you're in the setting where like you're sort of repeatedly extending a statement, right? Like we were kind of talking about before. What you can do, let's say you wanted to sort of do recursive composition and, you know, update kind of the previous proof with some new information. When you're recursively composing, you don't have to stick this whole v sub s in the circuit. Instead, you just put the update algorithm and vf in the circuit. And then outside the circuit, you sort of expose the proof state as like a public input. And then outside of the circuit, you can run vs at any given point to sort of finalize the verification. Right. So the kind of idea here is that somehow this like this proof state and this update algorithm and vs, they kind of work together in some way so that this accumulated proof state somehow kind of like encodes all of the other proof states that you had to run into VS also, and kind of lets you, you know, implicitly run, oh, this should be VS on the old proof states as well. So somehow, you know, by the way this update algorithm works, it works in such a way that the proof state it spits out, it includes it accumulates all of the previous ones as well. And as I mentioned, this is sufficient for recursion. You don't need a full snark, you just need an accumulatable narc or whatever for recursion in some sense, depending on what exactly performance characteristics are sufficient for your application. Because, as I mentioned, this gray outline you should think of as like a circuit. This is like the boundary of a circuit. So inside of your circuit, what you'll put is the fast part of the verifier and the update algorithm. And what you'll prove is like, I know a proof pi1 such that the fast part of the verifier passes, and I know the previous proof state such that if you feed that with pi1 into the update algorithm, the output is S1. And this S1 will then be a public input, which then the next time you go to compose, you'll prove, you know, I know a proof pi2 such that the fast part, you know, of the verifier passes on pi2, and also pi2 passed, you know, our recursive statement with output pi1, S1, and if you feed that S1 into the update algorithm with pi2, you'll get some new proof state S2. And so the whole time, you're never running this slow part of the verifier in the circuit until the very end. Let's say you compose one more time, until the end, you take this or cumulative proof state, this S3, and you do feed that into the final slow verifier. And because of how the accumulation scheme works, that is equivalent, more or less, to, in terms of the information content, to also having verified all of the sort of previous proofs. Cool. So does that, please people interrupt me as well. I'm going to try and keep an eye on the chat, but.
So just to clarify, at the end, you need to run both the last VF and VS, is that right?
Right, yeah.
Okay.
And I don't know, I have to admit, I actually didn't read that paper where they formalized this concept, so my notation may clash with theirs, I don't know.
I think that's roughly correct. The thing about that paper is that it doesn't formalize the bouncing between two curves, but I guess you haven't got to that anyway.
Yeah, I mean, I feel like in the formalism you can kind of hide that underneath like this is general enough to capture that under the covers. No, I don't know. Anyway, okay, so I don't know if I'll talk about that. It's somehow that's kind of hard to talk about. So right. So, and practically speaking, there's this fact from Halo, which is, if you have, well, I guess it's sort of implicit in Halo and then maybe made more explicit by that follow-up paper. If you have like an IOP, let's say, like an interactive oracle proof, an algebraic IOP, like where the messages are polynomials, like Marlin or Blanc or Sonic, and you have this, well, there's this particular inner product argument from which you can construct a polynomial commitment scheme, then you can build a sort of quasi-succinct recursive snark. I don't know if there's an existing terminology for this. Quasi-succinct kind of made sense to me, where the verification time is not constant or logarithmic necessarily. Well, the verification time is just different from the kind of verification time we usually talk about for snarks. So usually, you say something like the verification time is constant in the circuit size, or the verification time is logarithmic in the circuit size, or square root in the circuit size. Here, the verification time is linear in the size of a single sort of step of the recursion. And we can talk a little bit it's really easy to understand what a single step means from examples. Maybe if you haven't spent too much time programming with these things or thinking about them, then like it's not totally obvious. But anyway, cool. Oh, I guess I am going to talk about it. So there's kind of one hitch with this whole setup, which is right. This VF, it's not really monolithic. It really kind of splits into two little fast verifiers, one of which operates on a field F, and the other one of which performs operations in a group G. And the trouble with this whole recursive snark thing always is that this field F is not the base field of this curve. So you run into a situation where like only one of these is going to be efficient to put inside of a circuit. That they can't both be okay, maybe if someone wants to tell me about lookup, or whatever, we can talk later. But anyway, straightforwardly, like one of them is going to be really efficient, one of them is not going to be.
Even if you have lookups, it's maybe 10 to 100 times slower. So
okay, cool. All right. So right. So then there's this technique which we can call, say, deferring arithmetic, which is, remember before we had, what did we do inside of our circuit? We ran V sub f and we ran U, the update algorithm. So instead, what we're going to do is sort of, we take our V sub f, it splits into V sub math BBF and V sub math BBG, and we pull out the field part of it outside of the verifier, outside of this first circuit, and we only perform the V sub G part and the U part, and we we sort of expose the bits of the proof that are necessary in terms of in order to run this V sub F part of the verifier. And you want to try and be as clever as you can be here in computing like what are the parts that are really necessary, and trying to shrink that down as much as possible. because we'll get into it, but like you pay quite a price for public inputs. Maybe Dara has some scheme. I don't quite know what you all are doing with that, but so yeah, that's that. Now, now that we have maybe some idea, and if people are like, oh, I don't really understand anything you said so far, we can take a break here because I'm about to sort of change topics. Does anyone have any questions or?
You can roll in the sort of this pi I minus 1 limited to the stuff required for VF into the state SI, I guess, SQ or whatever it is, SI, right?
Yeah, you can. I guess you can think of think of it as part of SI.
They're logically separate, but yeah, you can bundle them together.
I mean, they don't have to be logic. I mean, if you like go to the accumulation scheme, this is basically you can make it as part of the accumulator, right?
So normally you want to make the accumulation scheme as simple as possible so that you can kind of plug and play between different accumulation schemes and they don't depend on the proving system.
I guess it just depends on how you want to define your predicate that is being accumulated. But anyway, sure. Yeah, sure.
You clearly can do that. It's just that if you want, for example, so when we're switching from Halo 1 to Halo 2, that's just changing the proving system. It's not changing the accumulation scheme at all. So it's convenient to be able to do that. But let's carry on.
All right. I will move on, I suppose. So, right. So now let's kind of talk about concretely, like what are some of the tricks to really optimize recursion in this setting. So I ran, just kind of for fun, I guess, I ran like an encoding of the circuit just using R1CS and the naive, like just reducing from R1CS, it was like 2 to the 20-ish constraints or something like that. And then with custom constraints for a circuit that, I only really know about circuits that verify 2 proofs. And I think I have a profile from one that verifies 1 proofs. I don't quite remember. For ones that verify 2 proofs, it's like 2 to the 17-ish, with a little more work, it would be 2 to the 17. But right now, like 2 to 18-ish constraints. So like quite a big factor. What's important to look at, you always want to just look at like what are the main operations that are being performed and just optimize the heck out of them. So there's hashing from the sponge in the Fiat Shamir. There's scalar multiplications. There's like this endoscaling thing. There's unpacking fields into bit strings, and then there's checking Booleanness. Actually, I prefer Booleanness than Booleanity of bits. And thankfully, like due to how Plonk works, this is mostly free in almost every instance, which is really cool. So let's like this is a flame graph of the actual circuit that does what we saw before with the VF, V sub F, and so on. Let's like just take a look at it just to kind of get a concrete feel for what things look like. So you can see the whole thing is like, oops, it's like 85,000 constraints. Oh, shout out to Matthew for making this awesome flame graph tool. It's great.
That is really cool.
Isn't this great? Yeah, I don't know how I would have like fixed all the performance bugs without this. So right, so we didn't talk about it, but so okay, there's this technique. I feel like everyone knows about it by now, but maybe not. Which is like you sort of alternate, because there's this mismatch between the field and the group operations. You like alternate circuits from 2 different proof systems, which have sort of matched, like the field of one is the group size of the other, and the group size of the other is the base field of the one. So you sort of go back and forth. So this first bit here is like running V sub F kind of on the previous guy's pi restricted to F or whatever. This is probably longer than it should be. I don't know, 10,000 constraints seems like kind of a lot to me. this this is like processing the public inputs, which are like these deferred values. You can see it's like a real waste of time. So, you know, there's so many public inputs. I don't know, 1, 2, 3, 4, 5, 6, 7. It's like 20 something. And these are a bunch of scalar multiplications, all these little purple blocks. This is hashing, these little stripes here. That's like in the sponge, that's fine. And then this bit is the inner product argument verifier, like the V sub G, the group operations part of the inner product argument verifier. You have some scalar multiplications. The Planck verifier has to do some scalar multiplies. And then this, you can really just look at this and see that, well, if you thought about it long enough, or if you had to work with it long enough, you can really look at this and just see the inner product argument verifier, because here, you know, this bit here is like computing all the challenges for one per round, and this bit here is doing all of the endoscalings in the kind of logarithmically sized MSM or whatever.
18 rounds, right?
Yeah, this is like 8. We can count. 1, 2, 3, 4. No, okay, count. Cool. So that's just, you know, gives you a flavor of like, okay, what's left to optimize, blah blah blah. There's definitely like a lot of room to fix like I feel like this being 10,000 constraints is absurd. Like that just should not.
Your intuition is correct.
Yeah. Let's see what else. We haven't spent much time on like we've designed custom constraints for like different column numbers or whatever, but this is just using 3 columns. And so I think probably if you use some other number of columns, you can probably get better performance, but whatever. Yeah, otherwise, I don't know. So let's see, moving on. Let me just, you know, probably not that many people have really spent that much time with kind of Planck style custom constraints, so just some notes. What these are for is for letting you take advantage of a repeated structure in your circuit. So like, as you can see, like the circuit is very repetitive, right? Like it does a bunch of hashes, it does a bunch of like scalar multiplications, it does a bunch of these like endoscaling things. Like the fact that you can just like, you know, make a flame graph and just like see all the components of the circuit tells you that the amount of like kind of one-off logic is like pretty low. And as we said, you know, what are these repeated things like scaling, endoscaling, running the Poseidon hash function, and packing bit strings. Actually, we didn't do this yet. There's a lot of performance to be gained from doing that. Or, you know, just any operation performed frequently.
There was one little question in the chat, by the way. Maurizio, do you want to say it?
Maybe I can open the chat. I suppose these timings are just for witness computations. Oh, these are actually constraints. So, yeah, this is like, it's not really time. It's just number of constraints. Does that make sense? So like it says milliseconds, but 1 millisecond equals 1,000 constraints. Yeah. Cool. Yeah, we just reused the Chrome thingy. Yeah, with hashing, like, let me just talk a little bit about kind of the choice of the hash function. There's a few, you know, reasonable possibilities you could go with. Like, there's rescue, there's Poseidon. I guess there's Peterson hashing. I guess not really, because you need like random oracle, but I didn't. Yeah, I don't know. I didn't think too much about it. Rescue, you know, it has this this S box sometimes, which is like x to the. You'd have to take an alpha root for alpha equal to like 5 or something. You know, this is really slow on like a CPU. So this was kind of what ruled this out for us. And then also, let me just say, like, potentially, this is not a huge deal because like there's only 2 kinds of rounds, but the fact that there's this like alternating round structure, you know, sometimes you have x to the alpha and sometimes you have x to the 1 over alpha, that does increase the price that you pay in terms of verifier performance a little bit and verification key size, and I guess proof size a little bit. Yeah, for your final proof, because it's not totally homogeneous. So like the more homogeneous, the better. Poseidon, it only has these x to the alpha S boxes. This sort of, you know, usual way is they did this partial rounds thing to try and make it more efficient on CPU. But the thing is, it's already way more efficient than rescue is because of these x to the 1 over alphas. So actually what we've done is it makes sense both from a security and prover performance, circuit performance perspective, is we just don't have any partial rounds. So like only full rounds in our Poseidon. And that is better because you have a more homogeneous circuit structure, so you don't pay, you can save on verification key size, proof size, verifier time a little bit.
That's interesting. I think if you go with a larger number of columns, then you can pack a full rescue round, so 2 steps into a single row of the circuit for a Planck style circuit.
Yeah, that makes sense. We haven't.
But it's still really expensive to compute outside the circuit.
Yeah. Cool. So let me tell a bit about this endoscopy technique, because I think actually this technique is actually really useful. And this is something that Sean and Dara, and I'm not sure who else came up with. I think this was something
me,
like that people used to spend a lot of time on using like curve endomorphisms to speed up scalar multiplications and stuff, but it's really useful inside of circuits. So what's the idea here? The idea is there's some function like phi, which takes a bit string and a group element and gives you a group element. And this function, it's equal to some other function just of the bit string, which maps like into the scalar field of G times G. So it's like this function, like somehow it lets you compute a scalar multiplied by some scalar which is related by var phi to the bit string S. And this function var phi is injective on small enough inputs. Or small enough, I'm not sure what it is, but it's small enough.
Yeah.
So why do you care about this? Because actually this capital phi is more efficient than just like straight up scaling by a number. And this is good whenever you can use this wherever like the specific number that you're scaling by doesn't really matter. So for example, if very often in elliptic curve or whatever D-log group based protocols, you scale something by some random challenge. This is a perfect setting for this optimization because you don't really care what the challenge is. You just care that it's sampled from a large enough set of distribution of possibilities. And for those who are familiar with this inner product argument thing, like you have these challenges like xi and well, depending which one you're using, it could either be xi squared or maybe just xi vanilla to the 1. And so, in that setting, yeah, it's great because these don't have to be like a real, these don't have to be like a real scalar multiplication because you don't really care what the xi's are, you just care that they're sort of have enough entropy. And because this var phi is injective enough, or injective on small enough bit strings, then it will have enough entropy.
By the way, if you want to compute whether it is injective on a given curve, there's some code in Dara/Tweedle to do that.
Cool. Right. So unfortunately, sometimes you don't have total control over the scalar. And it's like, it has to be some specific thing. And so you want some fast ways to do scalar multiplication. Dara has given a fast algorithm for the following function, which is scalar multiplication, but then you have this kind of thing that you need to correct for, which is like, you want to do t times g, but this algorithm doesn't let you do that. It lets you only do t plus 2 to the size of t in bits minus 1 times g. So you need to come up with some way of kind of correcting this. And there's, depending on the exact setting, there's a bunch of things you can do. Often, when S is part of the witness, you can replace it. You can just replace it with S minus 2 to the n, and just kind of witness that instead. And then as long as in that setting you won't hit any of the edge cases, this is fine, and you can just compute S times G this way. The other way of doing it is if the base of the scalar multiply that you want to do is sort of statically known or almost known, known up to a small amount of computation that you need to do to disambiguate, you can also just pre-compute this correction of like 2 to the n times g and just kind of subtract it off at the end. Cool. So now that's just kind of on optimization broadly, and at the end we'll visit like, okay, what are some other optimizations you can do and so on in the future. But let me just talk a little bit about programming with recursion now, because this is really, in my opinion, like the best interface. And if people ever like write other libraries in other languages, I hope that they use a similar interface, because I think it's great. Okay, so like let's see an example of actually using the recursion library. So let's say we want to prove statements of the form, or statements which are like, the public input will be x, okay? And what we'll prove at x is of the form hash of hash of hash of hash of hash of hash of 0, some number of times, exists a number of times such that x is of this form. So here's how we do it. We give basically a set of inductive rules, you could say. So the first rule just says, okay, this is a public input. The first rule just says x, x is of the correct form if it's equal to 0, right? Because then that's of this form with hashing 0 times. And then the second rule, inductive rule, just says, okay, assuming that we have some x prev of this form, then x is of the correct form if x is equal to the hash of x prev. Okay, does this more or less make sense to people? Does that scan? Yeah. Is it confusing? Maybe
I really like it.
Gotten used to it. Sorry, go ahead.
I really like it. I'm going to try and make our implementation of Halo 2 do the same thing.
Oh, cool. Awesome. Yeah. Yeah, I think it's great. And then, what happens is you get 2 provers corresponding to each of the 2 rules. So the first prover, the base prover, that will let you prove according to this rule, this first rule. And the second prover, inductive prover, will let you prove according to this rule. And for each one, you sort of declare like, okay, how many previous instances of other proofs do I depend on? And it's really cool. Like, it lets you compose like across different proof systems with different verification keys, and anyway, whatever. Cool. So, right. So let me just say a little bit about like the underlying kind of formalism or whatever of this library. There's this formalism of kind of an inductive rule, which an inductive rule, it says how one can turn previously proven statements into new statements. For example, these 2 rules. So you sort of declare, what are the previous statements that I depend on? Here, I don't depend on any previous statements. And how do I get from the previously proven statements to the new one? It's this description. Then, same here, I depend on one previously proven statement of type, myself. And this explains how to do that. And I think this is a nice, like this is kind of like, I guess, the same thing as what people call PCD. But I guess, I don't know. Well, I guess all I can say about this is it lends itself to easily writing programs described in this way.
The presentation in the PCD paper is not that easy to follow.
Yeah. And this kind of language, being able to talk about like sets of inductive rules as defining a proof system, you kind of need it to talk about performance, because, for example, like the complexity of the verifier for a recursive snark system, whatever, is the maximum of the complexity of the inductive rules defining it. So you need to be able to say things like that. And this is like when I talked about before, like one step of the recursion, it's like one application of one of these inductive rules. So we used to use Marlin instead of some kind of Plonk system as our underlying proof system. And I just wanted to share, for the benefit of others, some lessons on what was good about Marlin, what's good about Plonk. Marlin is, I think, much friendlier to compilation from R1CS, and the reason for that is In Marlin, the cost for the prover is the maximum over like your 3 matrices, your A, B, and C, of the number of non-zero coefficients in that matrix. Okay? People know what I'm talking about? I know Pertush is here at least, so at least Pertush knows what I'm talking about. But this is really nice because it lets you sort of, when you have a constraint and you're reducing from a rank 1 constraint, you can choose, where am I going to put the non-zero coefficients? Am I going to put them in A? Am I going to put them in B? Or am I going to put them in C? And you can do that to make them as balanced as possible. Do people see what I mean? Because you're taking a max, like you want it to be perfectly balanced. Do people see what I mean?
Yes.
Yeah. So, you know, for example, like, let's say you have a constraint that's just like x equals y, okay, where x and y are some linear combinations. There's so many ways that you can reduce this to like a, you know, coefficients in the Marlin matrices. You can do x times 1 equals y. You can do 1 times x equals y. You can do y times 1 equals x. You can do x minus y times 1 equals 0. And each of these lets you put the non-zero coefficients in different matrices. So like this one lets you put it in A and C. This one lets you put it in B and C. This one lets you put in A and B. So, you know, in practice, our circuits were like basically perfectly balanced. You know, the discrepancy between the 3 matrices was like in the low hundreds, maybe. I don't even remember. It was just very small. So that was a nice thing. But, you know, Planck, Marlin is okay, but Planck really has a much higher optimization ceiling with custom constraints. And there's no reason why you couldn't use custom constraints with Marlin, but it's a bit awkward. And anyway, what you're really paying for is the sum check thing or the lint check, whatever. And you know, if you're not really using that, then there's not really that much of a point. Yeah. And the other thing is that there's fewer evaluation points. And I know there's some variant of Marlin that lets you eliminate one of the evaluation points, but still, which that leads to improved efficiency for the verifier and also better proof size. Cool. So like some future directions here. One thing that I'm really curious about is combining these with like air Starks. This is what most people just call Starks, but like the proof system that we just talked about is also a Stark, so I call it air Stark. This is like Starkware TM Starks. Other kinds of custom constraints, as I mentioned, there's like a few operations that we have yet to custom constraintify, like bit packing. I'm also still kind of curious about brute force recursion, like with lookup or whatever, so you don't have to use the cycles thing, because as you can see, like half of the verifier is like dealing with the public input from the last one. So if you don't have to deal with that, like that would be cool. And then like on the kind of library side or software engineering side, at some point there will be a WASM improver, so you can just run it super easily in your browser, and also like a JavaScript interface for this whole recursion library. Right now it's in OCaml, and I showed it in Reason syntax, so it kind of looks like JavaScript, but the difference between kind of JavaScript and JavaScript, I think, is like a step function. So for most people, so yeah. Let me just talk about like a little bit about Snaps, which is our like kind of facility for computation. Mina. Yeah. So what is, you know, what's the idea here? Okay. So like just broadly, probably everyone's already on this page, but I made these cartoons, so I'll just use them. So like let's say you're a computer user. You're using your computer, it's cool, and it's great because you're using like open source software. So you're really happy, like you can look at your computer, or you can look at the program your computer's running, you know it's not doing anything nefarious, and you know it's just doing some pointer stuff or whatever. So that's great. But this is kind of not reality, because what is the reality? The reality is that like your computer is just kind of a thin client that really just sends your data off to some daemons who then, I mean, you have really no idea what they're doing with it. You don't know what computations they're running. You can't look at them. You can't look at the source code, blah, blah, blah. So that kind of sucks. But what's cool about Snarks is they let you kind of force these daemons to become on a human scale. And you can have kind of the same or a sliding scale of the same visibility into the kinds of computations they're performing locally with, so that's kind of the, like at a high level, like on a societal level, I guess, like why are snark-powered verifiable computing privacy applications useful. And concretely, like a snap in Mina, what does it have? It has like a state. So this is some small number of field elements, and some kind of transition function or really transition relation, which comes from a snark circuit saying how is that state allowed to be updated, and then some other stuff which kind of controls, which lets you deal with the kind of asynchrony of this model that I didn't make any slides on, but I can talk about. There's lots of cool applications you can think about, like flexible private elections in many settings, having sort of private computation happening kind of quote unquote on chain, or at least being verified on chain, and I think another cool one that I'm excited for someone to build at some point is like partial information peer-to-peer games where you use snarks to sort of like, as like moves in the game kind of be revealing partial correct information to the other player. And it's the most important thing for all of these things is having no setup, or at least having universal setup, I suppose. Because if you don't, like, come on, I mean, you're not going to run a ceremony for every new smart contract. It doesn't make sense. I think that's all I have slide-wise. Yeah, but we can chat or whatever if you want to.
Cool. Thank you.
I clap.
So yeah, are there any more questions or thoughts?
You went over the comparison of the Marlin-based and the Plonk-based quite quickly. Didn't quite have time to
Oh yeah, you want to chat about it? Here,
yeah.
let's go right here. Oh, this slide?
Yeah. So yeah, I mean, it's clear that you have to do, at least with the current state of the art, you have to do more work designing your circuit for Plonk, or at least because to get the full benefit of it, you really need to use custom gates. So yeah, I guess there is that trade-off. So do you have numbers on how much the verification circuit costs for the Marlin-based one and the Plonk-based one?
So I only really remember for things that have two verifiers inside of them.
Yeah, that's a typical case.
Yeah, and just for the benefit of everyone else, there is something that's kind of quadratic that you have to do that's sort of quadratic in the number of verifiers that you stick inside of your circuit. But so with Marlin, I think the domain was like for the number of non-zero coefficients was something like 2 to the, I think it was like 2 to the 19. Okay. And with the Plonk one, right now it's just above 2 to the 17, and like we'll probably push it down to 2 to the 17.
Okay. Yeah, I think that corresponds quite well with figures for circuit size that I've seen before comparing Marlin and Plonk.
Yeah.
Yeah, so that's not a surprise to me.
Izaak, was that with sort of the new version, which has like only 2 sum checks, and with the sort of row call optimization as well?
It was with the row call optimization, not with still with the three sum check rounds.
Okay. All right. Yeah, since then there's been like a few optimizations also to the basically how you handle the opening, so that you're actually opening, you transmit fewer evaluation points and you do fewer field operations. That might also reduce the sort of verification cost.
Right.
Because so Waking, one of Ali's students, has been, and Nick and other folks have been implementing a Marlin verifier, like standard PCD style, BCTV style, and they get something close to, I think, 300K constraints using the KZG10 style polynomial movement.
Mm-hmm. Yeah. Even with the inner product argument one, it wasn't that much. It was maybe around 300K also. So maybe I should try and share my optimizations with you guys. I don't know, because you could probably get it to be lower.
Yeah, so it's yours. That didn't do any accumulation. So I think, yeah, once you account for accumulation, you come down.
Yeah.
I mean, I don't want to be too negative on Marlin. I definitely think that's a line of investigation that needs taking further.
Yeah, no, I think there's lots of interesting avenues there. I think Marlin, I think that generally you can sort of combine these polynomial algebraic IOP kind of systems to just have, you can combine airs with Marlin or Planck custom constraints with like the Marlin side, where you can just share the witness polynomial across the systems.
Right.
Fairly. I haven't thought about it in enough detail, but I'm sure something to be said there.
One thing I'll say about Marlin and Planck, I had this idea, and I don't know where I got it from, that Planck would just be faster, like even without custom constraints than Marlin, and that was definitely not the case, because the reduction from R1CS is so nice with Marlin.
Yeah, basically in Marlin you don't pay for like sum of like the total number of addition gates. You pay for like sort of the max of addition gates across the 3 matrices, whereas in Planck you pay for like the sum of the addition gates.
Yeah, and in practice, because you can balance things so well, it's basically number of addition gates divided by 3.
Yeah.
I mean, I think of it as there being a trade-off between engineering effort and performance. So with Planck, you need to put in more engineering, but you get a smaller circuit out. But we'll probably have compilers that can do that for us eventually.
So you mentioned that there are 2 verifiers usually. What are the 2 verifiers?
Say that again?
So you mentioned that you usually verify 2, I guess, proofs in every step. What are the 2 proofs?
Oh yeah, so in Mina, we're we basically do proof composition in a tree. So it's like there's a binary tree of proofs, and you're composing up that tree. Does that make sense, to kind of compress history?
Got it. So yeah, now I'm curious about your comment, because you said it's commonly what you do.
Say that again. Sorry. Go ahead.
That will probably be what we end up doing eventually, anyway. I was interested when you said that there was a quadratic dependence on the number of verifiers.
Oh yeah.
Why is that?
I'm trying to remember. So let me remember. Okay, okay, I'm not gonna remember completely, but basically, each proof has to expose the the field restriction of the 2 proofs that are inside of it, right? Okay. You know what I'm saying?
Yeah.
And I don't remember. I could look at the code, but because there's a part in the code where there's like a vector of vectors of something, and the length of the vector is equal to the maximum number of verifiers inside of a circuit. I can find it easily if I look at the code, but it's hard for me to remember off the top of my
head. The reason why it didn't occur with my intuition is that if you think about something like the BCTV14 recursion. In that case, you're needing to do some pairings, but you can, whenever you just need to compute a pairing product, you can just do a single final exponentiation. So it actually ends up more efficient to do multiple, say, GROT16 verifications.
Right. Yeah. Let me. I can take a look and get back to you.
Okay, cool.
Actually, Dara, if you don't mind my asking, I was curious to hear, are you all, so like for public input handling, we just compute the polynomial commitment to the, we basically just do like a multi-scalar multiplication to compute the polynomial commitment to, like, you know, the low degree extension, kind of the low degree extension of the input. Do you know what I'm saying? But you all have some
yes.
Peterson commitment or something, which is an alternative to this?
I don't think we've exactly decided what the most efficient way to do it is.
Okay.
Yeah.
Okay, cool.
It's not obvious.
Yeah. Yeah, yeah. You can see from the flame graph, it's like a really crappy part of the circuit.
Let's go back to the flame graph, because there were lots of interesting things there. Just tell us what the various pieces are again.
So this is running like the field part of, like, finalizing the previous guy's proof.
Yep.
Doing the arithmetic. This, what is, I don't know. This is a sequence of, I think, endoscalar multiplies. I don't remember what it is here. This,
okay.
And then like this bit from like 15 to 20. I don't remember what that is. This is,
well, there's one per round, it looks like. So
oh yeah,
that must be challenge processing.
I think that shows up later. So I'm yeah, whatever. We can look maybe at the code, but this is I believe this is computing the commitment to the public input polynomial.
Okay.
That's
expensive.
Yeah, super expensive.
Yeah.
So you can save because like a little bit, because like a lot of the elements are just challenges. So like, you know, that obviously is less costly. But yeah, super expensive. This I think is just running the sponge. So that's actually really cheap. So this is just like running the Ditchner.
Yeah, either Rescue or Poseidon are really, really cheap in this.
Yeah. And then this is the inner product argument. So, oh, actually, sorry. This is in Plonk, you compute this commitment to like this, I think it's called F, this F polynomial. And there, like, the complexity depends on how many kinds of custom constraints you have, but that's what this is. So yeah, I guess if you have fewer kinds of custom constraints, that's better. And yeah, this is the actual running of the inner product argument verifier. So you have a bunch of, I have to remember what all these are. I'm a little confused on what this block in the beginning is, but this is, I guess this is running the sponge for the inner product argument.
Yeah, it looks like there's a lot of overhead each time you do that.
Yeah, maybe, I think that's from like unpacking. I think that's from unpacking bits and using like only the low bits for the challenges.
Yeah, maybe paying more attention to optimizing that.
Yeah. So yeah, like that'll probably go away when we implement the bit packing constraints. And then these are the endoscalar multiplications, and then there's a few scalar multiplies that you have to do in that verifier as well.
Right.
So
I see. Okay. Yeah, I mean, it's not, there's not obviously one huge chunk that, well, I mean, I guess the processing deferred values is the biggest chunk.
Yeah.
That looks as though it might
And Izaak, we're still experimenting with Marlin. So we've got, the idea is gross 16 on one hand and Marlin on the other one. So we haven't looked into Blanc yet. But can you tell me something about the form of these custom gates? So degree, variables,
Oh, so right now, our gates, this is definitely not optimal at all. And I think there's probably like 1 or 2 factors of 2, like a factor of 2 to 4 to be picked up by optimizing how we set this up. We have like 3 columns, and each custom constraint, I think the max degree of one of our custom constraints is like 5 or 6 or something, which kind of sucks because then you like pay for this big FFT, but actually that's not the dominating part of the prover, so whatever. Yeah, so like given that we're already on one of the custom constraints, going up to degree 5 or 6, I forget what it is, I'm sure there's like other stuff that we could be doing in the other ones to take advantage of that, because you pay for like the max degree.
and how many?
Sorry?
How many different?
So we have constraints for, what do we have? There's scale multiplication, there's Poseidon round, there's the endoscaling. The scale multiplication, I think that has 2 constraints associated to it, 2 or 3, I forget. The endoscaling, I think, has 2 or 3. The Poseidon, there's just 1. Then, I mean, bit packing will just be 1. Yeah.
Thank you. And overall, I mean, what has been the improvement that you've seen moving from Marlin, although you were with the old Marlin maybe, but
yeah. So right now it's been a factor of like between 2 and 4. I think it will be, we're very close to the next power of 2, so then it will be somewhere between 4 and 8. So pretty good.
It's very huge.
Yeah.
Cheers.
Yeah.
Thanks.
I think Sean said that there were 2 sweet spots in the max degree 5 and max degree 9.
Oh, okay. That's interesting. Yeah. What is that based on?
I don't remember.
Okay.
How fast does the verify, like it says 85 milliseconds, how fast does it need to be, or what's the?
Oh, so this is actually, we repurposed the Chrome debugger for profiling constraint systems. So 85 milliseconds means 85,000 constraints.
Gotcha.
How fast does it need to be? I guess that depends on your application. Yeah. Can you?
I just haven't played with this tool. It looked like a beautiful tool, and I saw 85 milliseconds. I was like, how fast does it need to be? So I think I just need to play with it.
Oh yeah.
I think it leads to my next question. Like, how do we get started? Like, how do I start playing with tools? And do you have like an example that we can play with, or is it still?
Oh, that's a great question. I think, let's see. Well, what's your level of comfort with OCaml? That would be the first question.
Play with something for a hackathon, but that's kind of the extent of it. No.
Who was asking also? I can't see, just so I know.
Adrian?
Okay, yeah. I think the best thing to do would be to wait until there's JavaScript interface, which shouldn't be too long. Yeah, should be very easy to use. Before then, I mean, the code is all open source, so like if you're really gung-ho about it, please, send me a message and I can try and help you out.
Cool. So I think now we've done a good session on Pickles, and I want to say thank you, Izaak, for putting this together and sharing this project and your awesome slides. There's been a lot of chatter all the whole time about the drawings, and they're really good.
All right. Yeah, thanks Anna for inviting me. It was fun.
Cool. And I guess if there are any links or anything that viewers might want to check out, just send them my way and we'll put them in the show notes
Okay.
to this as well.
Cool.
Cool. Thanks, everybody.
Thank you.
Bye, everyone.
Thank you.